All right, so let's start with the following example. So here, f of xy is a real valued function of two variables given by the formula x squared plus y squared. So the value of this function at the input xy is equal to x squared plus y squared. And we are specifying the domain. So here we are saying x is non-negative and y is non-negative. So this is a way of specifying the domain of the function. So in this case, you can see that the domain of the function would be the collection of all points in the two space which are in the first quadrant, including the points on the positive x-axis and the positive side of the y-axis, and including the origin. So that's the domain of this function. Now, if we have this, this function is given without a specified domain, then we take the largest possible subset of the two space as the domain. So if you look at this function here, it's the same function as in the previous example, but the domain is not specified. So in this case, we're going to take the domain to be the set of the largest subset of R2 for which this formula makes sense. Well, you know, this formula makes sense or can be computed for any point in R2, and as a result, the domain of this function would be entire set of points in R2. So here we have the function f of xy is equal to x squared minus y squared divided by x squared plus y squared. So if I look at f of 4, 5, then f of 4, 5 would be 4 squared minus 5 squared divided by 4 squared plus 5 squared, which would be 16 minus 25, so that's negative 9, and 16 plus 25, that's 41. Now, what's the domain of this function? Well, again, the domain is not given, so we take the domain to be the largest possible set of points, largest possible set of points in R2 for which this formula can be computed, or this formula can make sense. And since this is a ratio, notice that the numerator makes sense for any xy and the denominator makes sense for any xy. Now the ratio will make sense for any xy as long as the denominator doesn't vanish. So notice that when x and y are both 0, we get a 0 in the denominator, and that's the only time we get a 0 in the denominator. So the domain here would be the set of all points in R2 except the point 0, 0, that is except the origin. So the domain here is the entire plane except the origin. So this symbol here means that from R2 we are getting rid of the point 0, 0. Okay, so the next function here is f of xy is equal to root of x plus y plus 1 divided by x minus 1. We want to know what's the domain of this function. Well, so again, we want to understand for what points in the plane does this formula make sense. Well, the root of x plus y plus 1 makes sense only when the root of x plus y plus 1 is real when x plus y plus 1 is positive, or non-negative. So we need x plus y plus 1 to be non-negative, and so that means that we need so first of all, let's figure out which points in the plane satisfy this inequality. Well, this inequality is the same as x plus y is greater than negative 1, or it is the same as y is greater than or equal to negative x, negative 1. So this inequality here is the same as this inequality here. We're going to get to this x not equal to 1 in a bit. So we're trying to solve this inequality here. And well, let's draw the equation first. So what is the equation? If this inequality is the equality, then what do we get? Well, this would be a straight line, and so this red line right here is the straight line. So what I have drawn are the x and y intercepts. So this is the y-intercept. So when x is 0, y is negative 1, and when y is 0, x is negative 1. So these are the intercepts. So we can join them in a straight line. That's the graph of the equation. So now, this red line is the graph of the equation y is equal to negative x, negative 1. And so which points will satisfy this inequality then? Well, on the line y is equal to x minus 1, and the points above this line would be the points that satisfy this inequality. So if I pick any point here above this line, then that's going to satisfy this inequality. Any point below the line will not satisfy this inequality. Okay, so the region highlighted in blue is the solution set for this inequality. Now, at the same time, we don't want 0 in the denominator, so we don't want x minus 1 to be 0, which means that we don't want x to be 1. So notice that x is 1 along this green line. So x is 1 is a vertical line. So we don't want x to be 1. So what is the domain then here? So the domain would be all the points in the blue region except the points on the green line. So it is the set of all, so the domain is the collection of all points x, y in R2 such that x plus y plus 1 is greater than 0 and x is not equal to 1. So graphically, that's how the domain looks like in this case. What's the domain of these? What's the domain of the function f of x, y, z is equal to x plus y plus z? Well, this formula makes sense for any point in R3. So the domain here would be R3, the entire 3 space. What's the domain of the function f of xyz is equal to x squared minus sine of xyz plus yz squared? Well, notice that each of these terms makes sense no matter what xyz is. So sine can be evaluated at any real number. So xyz could be anything there. So we see that the domain here would be R3 again. Here we have a function of 4 variables where f of x1, x2, x3, x4 is equal to 2x1 minus x2 plus 3x3 plus x4. And in this case, we see that the domain would be the entire set of R4, and this is the 4 space, and the reason is this quantity makes sense no matter what x1, x2, x3, and x4 are. Okay, so I am going to stop here. In the next video, we will do another example. Actually, let's finish this example as well. So we want to find the domain of f of xyz is equal to ln of z minus y plus xyz. Well, recall that the log function here makes sense only when we evaluate it at a positive number. So z minus y must be positive for this thing to be defined. Now xyz makes sense for any xyz. So the only condition that we need here is that this function is defined when z minus y is positive, which means when z is greater than y. Well, so the domain would be the collection of all points x, y, z in R3 such that the third coordinate is bigger than the second coordinate. Now in terms of visualizing this domain, notice, so imagine, so if you draw the graph of z is equal to y, if you draw the graph of z is equal to y in the yz plane, then the points above this line will satisfy this inequality, right? So in the yz plane, the points above this line, so when I say above, I mean the points that are on the positive side of the z-axis, right? So the points that are highlighted in red, these are the points that satisfy this inequality z greater than y. Now in the xyz space, if you look at the plane that passes through this straight line here, so look at the plane that passes through this straight line perpendicular to the yz plane. So in other words, you're looking at the plane that is passing through the origin and perpendicular to the vector 0, 1, -1. And so if you look at that plane, then we are taking points above that plane. So the domain is the set of all points in R3 such that which lie above this plane. Okay, so that's the last example on finding the domain of a function, and then in the next video we will start to talk about the graphs of these functions.